All right, so we're now at chapter 8 now, and this is we're going to do this real quick. Chapter 8. I think we're going to finish. Yeah, we're going to finish this Monday. And as I mentioned, unfortunately, the book isn't finished because I couldn't finish it over break. So from here on out, we're textbookless. And God, I'm sorry about that, but there's absolutely no fixing it at this point. I had been slowly working on. So we're supposed to finish up with chapter 9, and it's all of about 2 pages. So sorry about that, but I did save you $250. So okay, so we're now in chapter 8, which are phase diagrams. And I've shown a couple, so I showed a phase diagram on colligative properties. I'm going to show it again. And it's, the phase diagrams even appear, if you are a book reader, then the phase diagrams show up a couple of times. And you've seen these in high school and in freshmen, so this isn't particularly anything that's going to blow your head off. And unfortunately, because I'm kind of out of time, I'm always going to show a P versus T phase diagram, but there are other phase diagrams. There's T versus V, or more accurately, density. Phase diagrams are also relatively common, and I don't think I'll have time to show one of those. It doesn't really matter that much, it's just a phase diagram. P versus T, we like P versus T because pressure and temperature are intensive, and hopefully you recall this. This is a very good, explain in words on the final. What are all equal? What things are all equal at equilibrium? You don't know. Temperature, take another guess. Give me one more. Chemical potentials. Now what do all those things have in common? Density. Density would also, wait, no, not density, sorry. They're all intensive. They're all intensive variables, right? So intensive variables are all equal at equilibrium. And that's why it's really sensible to show a phase diagram as with intensive variables. It just inherently it's a smart idea. You don't have to do it that way, but it just is a good idea. Let's see. So now last time, again, I just showed you. Now this is going to be universally true for. I'm going to draw the most general type. And again, I've not been beyond on previous exams of just writing this. Actually, not even putting P versus T, just drawing these lines and saying fill it out on test 3. Hopefully it's a giveaway. Remember, low pressure, high temperature, clearly you're in the gas phase. At high pressure, low temperature, you better have a solid. And then, of course, the liquid is the last man standing. Now, there is a, notice I drew this up arrow. That's because people are, we can build fairly simple devices to put materials under high pressure. We do that because we are humans, we like to tinker with things just for the hell of it. And we actually have, I mean, it's actually, I kind of want to spend a whole lecture on this, but we have simple devices called diamond anvil cells, which are exactly what they sound like. They're just 2 diamonds, and they're in a little holder. They're just like embedded in little metal plates. And they have screws. It's like a little triangle. And they have little screws that squeeze it together. And with your fingers, you can get to the pressure almost as the interior of the sun. I don't quite understand. I mean, I don't know. It's all mechanics, right? So twists, pressure, tension, Young's modulus, I don't know much about it. But you can reach ungodly high pressures. And then you can, because these are diamond anvils, diamond, you can also look through it. And literally people take pictures and of course more advanced spectroscopy. And we do that because, you know, for the hell of it. So we can map the phase diagrams of things to pressures that are, again, at greater than the center of the sun. And it's not even that hard. Okay, so that's why I drew a little arrow here, but notice I didn't draw a little arrow with the liquid gas. That's because it actually does come to an end. And we have the critical, I don't know if I can spell, we have the critical phase. This is a question mark. What is the critical phase? People, if you were to go, probably I bet chemical engineers more than chemistry, if you were to go get a PhD, you might do nothing but study critical phase this or that. What it is I can best describe what's happening is if I draw a point on the phase diagram, so let's say that this is like ethanol. This is not a water phase diagram, I'll explain why in a second. This is basically a phase diagram for just about anything but water. So let's say that I'm at that point there and it's a liquid. What would happen is if I, let's say I pressurized it. Okay, so the liquid pipe would get more dense. I'm cooling it and pressurizing it, but now I'm going to increase the temperature. And what's happening is, here, let me just draw a full circle. So that's my stop. Now what's happening is, I have a box. It's ethanol, right? Ethanol is in the box. I can change the pressure and temperature. Maybe this is a box because maybe it's like really high temperature and pressure. I got a window and I'm looking in. Okay, what do I see? I see a liquid. And then what I would see is it would turn into like a fog. And that's when I cross into the critical boundary. And then as I switch over to the gas, that fog would just kind of disappear. In other words, it would look something like this. I would have a, okay, here's the box and there's a window. So let's just say the box is transparent. I would have a liquid phase. Okay, then as I cross to the critical boundary, it literally gets just fuzzy. It's hard to see. It doesn't look like a liquid, but it doesn't look like a gas either. You have this like nebulous boundary. And you'd be like, well, I don't know what the heck that is. And then as it turns into a gas, when it turns into a gas, it wouldn't look like anything. And so this is, of course, the critical. It wouldn't look like anything, of course, because it's a gas. The point, and if we were to measure like the density, it would, okay, I guess it would maybe increase at first, but then it would decrease and then decrease further. And it would be smooth. It would, go from about, maybe, density of water is about 1 gram per mil. Liquids like ethanol would be around 0.8, that tends to be around universal. So it would go from 0.8 to probably less because it, looks foggy. And then it would have a gas density. And it would change from like 0.8 to 0.1 continuously and smoothly. Unlike a transition here, let's go from the liquid to the solid. What would happen is it would be 0.8 to, it would gain in density, right? Because solids tend to be more dense. So it would suddenly jump up as soon as it's solidified. I mean, you know that, right? Your gut tells you that. But this critical phase is neither a liquid or a gas, and that's why all of this happens. It looks fuzzy. The density never jumps, neither does heat capacity. And then you can kind of loop around and become a gas. And of course, if you were to go from the gas to the liquid, you would see those discontinuities again. You would see the density. If you were to loop around, you would see it basically start to rain. It literally looks like that. You can find videos of this stuff on YouTube. It would literally rain, and the density would suddenly increase. The heat capacity would suddenly change. It would increase. And you would see that all within like 0.01 degree temperature change. But the forward process, you would not see that. So the critical phase is hard to describe. No one really, you may have even heard critical liquid, critical gas. It's because it's neither. It's both and neither at the same time. And so I'm not going to say too much about that, but the things that are cool about this, other than, okay, it's just weird, and that's really about all I can say about it. There's one or two cool things about it. One is that the properties of whatever is in that phase can change radically from liquid or gas. It's really its own legit phase. And the best example is xenon. Xenon gas, xenon is a heavy molecule, it's the heaviest Nobel gas, so it's a gas. But when it's critical, in the critical phase, it's more like water than being a gas. It actually can solubilize, what can you solubilize with water? You can also do it with liquid xenon. Except that xenon is expensive and it's also dangerous to put things at high temperature and pressure. But anyway, another example, CO2. CO2 in the critical phase is as good as tetrachloroethylene. It's just like tetrachloroethylene liquid. You don't know what I'm talking about, do you? What do you use tetrachloroethylene for? Dry clean. Where do you think I got this camo shirt from? Dry cleaner, right? That's what's used in dry cleaning. You ever had a comforter dry cleaned? No one? Well, I have too much money, right? So I don't have a comforter. The cat peed on it. God, the cat peed on it, so I had to have it clean. A comforter, a down comforter back from the dry cleaner, man, that was rough because all the solvent, I mean, it really smells like a chlorinated solvent. And it smelled like that for a week, so I had to like hide it. Supercritical CO2 is just like that, but it's not a chlorinated solvent. So guess what? There's still a big movement to transform our dry cleaning industry into a supercritical CO2 cleaning industry. Dry cleaning with supercritical CO2. Problem, it never took off because these things are still dangerous. If you look at any phase diagram, the critical region is typically at really high temperature and pressure, and it's kind of scary. If anything goes wrong with this equipment, it's kabammo for the people that work there. So anyway, that's all I have to say about critical phase. Let me also, I said this last time, I'm just going to redraw. You know what I'll draw a water. I'll draw a water one. I'm going to redraw this, and I'm also going to point out all the terribly interesting things that are hidden in a phase diagram. And don't worry too much about that. I'm probably not going to bring it up. Solid, liquid, gas. So I want to show all the things that are hiding in a phase diagram. Shockingly large amount of information. Now this is water, by the way, because the solid liquid slopes left. And I'm going to show you a little bit. That's because ice is less dense than the liquid. Now if you think like, okay, water dense is less, forget that. Ice floats, right? You know ice floats. In fact, if you Google this, apparently if ice didn't float on water, there would be no life on this planet because ice would have floated to the bottom of the oceans and would have messed up the oceans and no life. Anyway, it's kind of neat. Ice floats. Now that means that the solid is less dense than the liquid. And what this means is, the way to interpret this, and we'll get more into this later, it means if you pressurize something, you actually favor the liquid, right? So let's start here. We're in You could have said something. Yeah, I also noticed I kept babbling about problem set 8, how I had a freezing point depression question. I didn't, did I? And you didn't correct me. You know what happened? I uploaded the wrong problem set. I got a zillion of these at this point, and I uploaded the wrong one. That's why I was rushing, because I thought I uploaded last year's problem set, or 5 years, I don't know. Please don't let me do that, okay? Because it kind of impacts you, especially if I'm telling you stuff that's wrong. Okay, now that I think we've established our relationship better, let's go forward from here. Okay, so, all right, so let's say you're here and you've got ice. If you pressurize it, you can go into the liquid phase, right? That's kind of obvious at a single temperature, right? Don't mess with too much stuff. Whereas, let's call this ethanol, that wouldn't happen. In fact, you'd be more solid-y. Now, the reason is I always like to express things as Le Chatelier's principle because that's kind of neat. I kind of like humanizing chemicals. You know, you try to change it and it fights back. That's like people, and so I kind of like that. And we always find that behavior in a lot of stuff. So what happens is, and I had to think about this. If you're pressurizing it, it doesn't like it, so it wants to depressurize. The way to do that is to occupy less volume, and to do that would be to go into the more dense phase, which is the liquid. All right, you follow that? I know it's a bit of the blah blah blah. It's a lot of stuff. Again, if I pressurize it, it can depressurize by changing phase by occupying less space, and that in water's case means becoming a liquid because water is weird. Anyway, all right, so now all the things that are hiding in a phase diagram. Let me, okay. The one that is the most well hidden is this one. drop to the gas line. You're in the liquid phase, so you drop to the gas line, and what you get here, and I'll just go ahead and call it water. It's technically for all water-like chemicals. Let's just call it water. Okay, that's the pure partial pressure. Now, of course, let's assume that this pressure is 101.325 atmospheric pressure. That's fine. But again, the phase diagram is designed to also tell you the pure partial pressure. I just think that's kind of cool. Okay, the other neat thing is that you can also read out the vaporization or boiling temperature. That's there. And I always say this one for last because it kind of gets in the way. You can also read off, of course, the melting temperature. Just right there. And there you go. Now, that's all I really have. Now, on the homework question number 1, I have you look at a water versus a non-water, call it ethanol phase diagram, and make some statements about melting point depression upon addition of salt. Water, actually, I designed that question. That's the reason I sent you a PDF as opposed to questions from the book, is that I'd come up with some new questions. I always try to do that every year, just because it just feels like I'm not doing my job otherwise. And you guys, you respond to different things. I said in class that water was unusual. Water's unusual about how the melting point drops like an unbelievable, minus 20 degrees, that's a lot. And I got fascinated why that was, and it turns out it's because of the way water has a less dense solid phase. So anyway, so this should help you with number 1. It's incredibly easy. Okay, last bit I want to point out is, okay, so here water, let's say that's 1 atmosphere, 298, and water is in the liquid phase, right? Okay, so I brought a demo, and I meant to bring a clear glass, but I brought this one instead because I forgot. So it's full of it's full of water, full of water. Okay, so we're maybe a little bit less than 1 atmosphere pressure today. We're a little high up, right? And it's well, it's probably about 25 degrees here, maybe a little bit warmer. Okay, so the liquid it's water. It's a liquid. Okay, now let's let it come to equilibrium. What happens? And we can just stay and wait. It'll take about 3 days. What's going to happen to this liquid? It's going to evaporate. Right, it's going to evaporate. And it's going to be gone. So now you agree. In 3 days, this is gone. Now you know things take time to reach equilibrium. So what the hell? Now think about it. The phase diagram of water is liquid at 1 atmosphere and 298 K. It's a liquid. But I know if I wait long enough, I'll have a liquid. And then we know it takes time to reach equilibrium. So what the heck is that? Huh? Which is it? How could it, the whole thing will turn into, the whole thing is going to turn to gas. And it probably won't even take that long. Any of you resolve? Why would that happen? Yeah? Hopefully you're like, what the hell, right? I mean, seriously. This is going to be in equilibrium in the gas state, but that doesn't make any sense because you've always been told that liquid water is a liquid. Any idea? Any idea resolve? Look, I have to admit, in other classes, people are looking at me like this, because they're like, wait a minute, that's right, what the hell? Okay, people are sleepy. Anyway, here's the answer. I blow over it. Right, now what do you think the partial pressure of water is in here? Well, no, the partial pressure of water is probably, well, it's not 1 atmosphere, then we would be underwater, by the way. It'd be raining. The partial pressure of water in here is less than the pure partial pressure. So that means if I do this, the system responds by evaporating a bit more to reach equilibrium right here, because we tend to dehumidify the buildings. And so it's not, the reason that you will have a gas is that we never reach equilibrium because we have a dehumidifier that's putting our partial pressure too low of water. And so it literally just evaporates away. Now here's a question, here's another question. Why do I have, and that, so some of it vaporizes trying to reach equilibrium. It can't because of a dehumidifier that's being powered by a power plant that's run on coal that was created by energy by the sun. And all of this is true, by the way, nutty but true. Okay, now I ask you this. Well, let me ask you a harder question. How is it that any of that liquid turns to gas to begin with when you're in the liquid state? Aside from the fact that it's trying to reach the correct partial pressure, and it can't because of our dehumidifier. How does any of it turn to a gas to begin with? Now remember that the gas has to be at 100 degrees C. That's true. So I ask you this, are some of those water molecules actually at 100 degrees? What do you think? Now, so for those of you who aren't playing video games, I actually saw a lot of this. What do you think? So some of those water molecules, to be a gas, it needs to be 100 degrees. Some of them are becoming a gas. In fact, all of them will if I wait long enough. Are they 100 degrees? Yes, they are. Wrong. Here's what happened. We're going to cover this in 346. It turns out that in this liquid, the water has a certain internal energy, yada, yada, yada. And they're moving at an average speed. We can sit down and calculate it. I don't know what it is, but it's probably kind of fast, by the way. But it turns out that there is there's a distribution. We're going to cover this in 346. It turns out that at any given moment, if we look at the top of this cup, so I'm going to exaggerate it. Yeah, okay, here's a water, here's a water, here's a water, here's a water. It turns out that some of them are hot and some of them are cold. And that's according to this, let's do this velocity distribution. Velocity would, of course, be its kinetic energy. It looks like this. It's actually really quite wide. And so, on average, let's say that this is 298K. There is a population in this liquid that are basically not moving, and that's like they're frozen, and there's some that are well above. I'm going to mix units just for the hell of it. There are some that are moving as though they are very hot. Simultaneously some are cold, simultaneously some are hot, and the average is the average. On average, they're not moving too much, so they remain in the liquid state. But a small fraction, because of just the way energy tends to flow around the solution, energy is always flowing in between molecules, and that's because they keep hitting each other, especially in the liquid state. What happens is, the reason you have a couple of hot ones is that all these SOBs, kind of like a group of chemical engineers, you guys beat up on each other a lot, I noticed that. A bunch of chemical engineer molecules took one and decided to beat up on it simultaneously. They all collided with the same one at the same time. This one suddenly became hot. Everyone hit it at once. It suddenly became hot and it happened to be at the surface. It got ejected out. And that keeps happening and happening. Right, so interesting enough, if we could shrink ourselves down, we actually only have to look at individual water molecules. If we shrink ourselves down and we look at an individual water molecule and say, hey, that one looks hot, that one looks cold, we'd be seeing some that are like, oh my god, this one's at 0K, oh this one's at 1000K, oh this one's at 298. More often than not, we'd say they're at 298, but sometimes we see a water molecule that looks like it's hot and some that look frozen. And if that hot one is on the surface, it gets out. Now the water cup actually freezes a little bit as a result, but because we have a, guess what, thermostat, we have a dehumidifier and a thermostat, we warm it back up and the process continues. Now because of the partial pressure of water being too low, dehumidifier, it wanders off and never comes back. And that is the unbelievably 10-minute explanation for why things evaporate. So anyway, I hope that was kind of neat, but that's why it works the way it does. And last bit, I'm going to go over, and there's other, you can actually see this behavior in other ways, and we're actually going to maybe end a tad bit early, have a normal break, and then again, please stick around. For those of you who are late, I'm going to cover question 3, how I designed question number 3 for maybe about a half an hour. I think it's actually kind of fascinating, so please stick around. Okay, let me point out another place you've seen this behavior. It turns out that one of the scariest things that ever happened to me was when I was coming back from college, and that was about 20 years ago. I'm just hanging out in the house and I hear my mom screaming from the kitchen. That's terrifying, right? I run in and my mom said, I don't know what happened, but the water exploded in the microwave. What happened was my mom put a cup of water in her favorite mug, heated it to boil, and was going to make tea. She heated it up, it wasn't doing anything, and when she touched it with a spoon, guess what happened? It blew up. Did any of you have that happen before? No, well, some of you have, some of you haven't. It happens. What happens is, if you have a cup of water, if you have a cup, and it's incredibly smooth, that was the problem. The cup was actually very, very polished. People who make coffee cups intentionally make them rough because of this phenomenon. They know that this happens. Because it was so rough, the water became superheated. And that's actually a manifestation of this behavior. So what happens is when something's about to boil, you get more and more of a population of these random hot ones. And what they do is, this is kind of cool, they end up forming little gas phase pockets. Little gas phase pockets inside of the liquid. And so it's mostly empty space, right? But anyway, they form these gas phase pockets and they form more and more of them. But these tend to nucleate off the walls. And that's just because there's like edges that give, that make it, it's like a nucleation site. It's like a catalyst. The edges act like little catalysts for the bubbles to form. So if you get water in a really smooth vessel, and none of these bubbles start to form, it won't boil. And you can actually drive the water temperature above 100 degrees without it boiling. You can also get water to go below 0 degrees and not freeze. The record, I think, is minus 63 degrees Celsius. Someone got water to be minus 63 degrees Celsius at Lawrence Berkeley National Lab, and it was still a liquid. They did it by taking this cup of water and shooting it out of this jet into a vacuum, and you know things cool in a vacuum? And it did cool, and so they did it in such a way that the liquid jet was really smooth, and then they used X-rays. You know how you characterize the structure of stuff with X-rays? You can do it on liquids too, so they verified it was a liquid. I was in the room when it happened, by the way, so that was kind of neat. I just told you what the grad school did. All right. Okay, so last bit, and then we'll actually end roughly on time. And this is kind of neat too. I think I have just enough time. I always find myself going over. We're going to go over what's called Gibbs phase rule, which is something to do with designing phase diagrams. So actually, one of you always reminded me to always point out what's the big picture. Why are we talking about any of this? For the remainder of today and Monday, what we're going to try to do is design a phase diagram. So what I'm going to try to do now is put together, I'm going to describe how it is I'm putting this together to begin with, this P versus T phase diagram. Why am I creating something with two axes, oh, did I get that right? For those of you who are late, watch the video, you'll laugh. Anyway, why am I creating a graph with two axes? Now, of course, I kind of have to because I have a board, but anyway. Why am I creating something with two axes and three phases that are all connected at one spot? You know, triple points where all three phases exist simultaneously. And so people study this stuff and they see that we have triple points. Anyway, what tells me to set it up like this? That's today's lecture. Next lecture will be, if I know the triple point of something, I have to have some experimental data. Kind of like the data table in the back of the book with delta G of formation. If you give me this, can I recreate the rest of it? Yes, I can. With equations, we'll derive that on Monday. With that, we basically can create a phase diagram with very, very, very little information. So that's the big picture. Now again today, what I'm going to try to do is describe the basic idea of how should I set up this phase diagram. Now don't take it for granted. I know at the beginning of the lecture I said, oh, well, we use P and T because those are intensive variables. That was actually just a starting point. Nothing said I had to do that. And anyway, it'll make a little bit, maybe this will make a little bit sense if I stop people like this. Okay, let me actually be a little bit more specific what I mean by that. Let's pick a point in the solid part. I am drawing this the way I am drawing it because I can change the pressure and temperature by some small amount and still have a solid. Right? Now, of course, I know if I keep heating it up, I'll get a liquid. Right, I know that. But this point can be changed by 0.1 degree and still be a solid. Right? So we won't be silly and talk about it if we go too far. Okay, now that means that I'm in a two-dimensional surface, and in a two-dimensional plot, it's just a plane. It's called a flat plane. Now, if I am at the liquid gas point, what happens is if I change, sorry, I didn't draw that right. Hold on one second. I didn't draw that right. If I'm at the liquid gas line, why am I drawing a line? I'm drawing a line versus a plane. I'm drawing a line because if I increase the temperature some dT, and I'm trying to maintain the liquid gas equilibrium, then I have to increase the pressure some dP. Now that means I don't have quite as much control. Here I can change temperature and pressure at will and still remain a solid. If, for whatever weird reason, if I'm trying to study equilibrium between a liquid and a gas, and I change the temperature, I can't do that at will, because if I just do that, then I've got all gas. So if I change the temperature, then my pressure has to change, and I don't have control over that. So that means I really only have 1 degree of freedom, 1 dimension, and 1 dimension is a line. 2 dimensions is a plane, 1 dimension is a line. Now, if I'm at the triple point, you cannot change temperature, you cannot change pressure. You can do neither. The triple point has all 3 phases in equilibrium. The slightest breeze, slightest change in temperature or pressure, will ruin that. You cannot change anything. Now notice that this information dictates whether I draw a plane, a line, or a point. Alright, so now hopefully that makes a little bit more sense of what I'm saying. I'm trying to figure out how to draw the graph, and then we'll figure out the equations for the line sets tomorrow. Alright, now this is called a degree of freedom. And it's called F. Now this is not degrees of freedom like can I rotate or translate from 2 months ago. This is can I change the pressure and temperature and still have a solid. Can I change temperature? Yes. But can I also change pressure? No. Because if I want to maintain equilibrium. Can I change temperature? No. Can I change pressure? No. 2 degrees of freedom, 1 degree of freedom, no degrees of freedom. And that's what I call F. Okay, F is 2 at least for temperature and pressure. I'm going to start there. But now obviously I'm going to have to start subtracting stuff off. Looks like I have to start subtracting some off because I described, this guy has 2 degrees of freedom. These others have less. So I got to take something off here. Okay, before I do that, let me think about, I'm going to add something here. I'm going to think of a phase diagram that, this is like an ethanol phase diagram. What if I did a phase diagram for water and ethanol? 50-50. I could do that. In fact, well, I won't even say it's 50-50. What I would do is, if I wanted to draw this, it would be painful. I would have to have mole fraction of water, and then in some other hyperdimension, I would also have to have some mole fraction of ethanol. Right? So again, what I'm doing is I'm trying to complicate this, and then I'll subtract some degrees of freedom off in a minute. You'll see what I mean. Anyway, okay, pressure and temperature, but I could also create phase diagrams with more than one component, and that means ethanol and water. And I don't quite know how to draw that, because if I do that, it looks like I'm doing this in multiple dimensions, and that's sucky. So I can't really draw that. Maybe I could render it on a computer. Okay, now the number of components is C. And so let's do water ethanol, that'd be 2. Again, I can't really even draw this. I don't even really know what one would look like, to be honest, to tell you the truth. But that means that if I can create a phase diagram, and I'm going to make it for something more complicated than just water or ethanol, I'm going to make it water and ethanol, then that means I got 2 more things I can change. I can change the amount of water, or I can change the amount of ethanol that I add. So that's 2 more things. Okay, now that I'm talking about mixed drinks, I could also put an ice cube in it, right? So I've got a liquid. P and T. I can change pressure and temperature. Of course I can. I can add in more ethanol, that's a degree of freedom. I could add in more water, that's another degree of freedom. I could throw in an ice cube. I could throw in an ice cube of water. You think of ice cubes as water, I could throw in an ice cube of ethanol. I could throw in an ice cube that I put in the refrigerator that was a mix of water and ethanol. In other words, everything I can think of as that's happening in the liquid can also happen in different phases. So again, recap, phase diagrams, I can always manipulate temperature and pressure. I can add stuff to it, and I can also add that in as a function of phase. That's just a fancy way of saying I could pour in, let's say that this is ethanol, I could pour in water, but I could also pour in an ice cube, or both, right? So you see what I mean? Now remember that we learned from ideal or non-ideal solutions that if I had, let's say I had a bucket of water, 50% water, 50% ethanol, and I also have some ice. Is the ice 50% ethanol, 50% water too? Not, it could be, but probably not, right? We know that if I have a 50% water, 50% ethanol solution, the vapor is not 50-50 because it's a non-ideal solution. Remember, it just doesn't work that way. No reason to think that a solid would do that either, right? So anyway, that's why you can't just say whatever the composition is of the liquid would be the same for the solid or the gas. In fact, I know for a fact that's not the case. Okay, so anyway, now last bit is I have to realize I've actually made a stupid mistake. I made a stupid mistake when I did this. I got this P versus T diagram of ethanol, and I said, let's pour in some water, right? And I drew that as another axis. Another axis that's coming at us, and that's kind of a complicated diagram. And then I even told you, like, oh, but then I have to have another one for the ethanol. You know, I add a certain amount of water, I add a certain amount of ethanol, right? 2 degrees of freedom. Or is it? If the mole fraction, so I'm making a phase diagram. 50% water, 50% ethanol. If it's 50% water, what is it of ethanol? If it's 25% water, what's the ethanol? 25. If it's 75% water, 25. So how many degrees of freedom do I have? 1. Right. Now, so hold on, there's a mistake. Mole fractions, and let's put them per phase. Mole fraction of component A. Now remember I told you about how I distinguish phases. I use Greek letters as a superscript. So let's talk about A and B, that's ethanol and water. per phase, the mole fractions have to add up. So that's the liquid. Let's do the solid. That'll be a beta phase. And then let's not forget the vapor. We've been talking lots about vapors lately. And that'll be the gamma phase. Okay, so no, you do not actually get to, when I mix two things into a solution, this is really counterintuitive. I want to say I have 2 degrees of freedom because I control how much of either I add. But, I mean, that's true, but it's simultaneously true that mole fractions add up to 1. And that means you truly do not have a degree of freedom. Also, this is, guess what, intensive, and intensive variables are the ones that matter. So what I see here is that when I started adding in, different phases, I started basically adding constraints. In other words, you know, the mole fractions had to add up to 1. So, so what I do is I take my degrees of freedom and I subtract constraints. That's kind of like I'm not really adding, you know, I add water and ethanol, that's 2, but it's really just 1, right? So I have to subtract 1. Now the way to figure this out, this actually gets a little bit more complicated because I could have water and ethanol and I could have liquid, gas, and solid, right? Now the way to figure this out is you write equations for your constraints, and then this is simple. You actually just add up the number of equal signs, and you subtract that number. Okay, so now what do you think? Should I subtract 3? It looks like I should subtract 3, right? Well, hold on, I have 3 equal signs. No, equal signs. I have 3 equal signs. Right? So that means that these are things I don't control. I don't control that mole fractions add to 1. And each equal sign is therefore a constraint, so I subtract 3. Right? That actually is the answer, by the way. But why don't we make it a little bit more generic? There's actually P. P is the number of phases. Notice that alpha, beta, gamma. I had to add a constraining equation for each phase. In my example, I had 3 phases. So anyway, just careful. Okay, last bit. I also, although this is a complication we don't tend to explore, multi-component phase diagrams. I might say a little bit about it at some point. I also have to know whether I'm talking about what phase, solid, liquid, or gas phase. Now, at the beginning of lecture, I said that there were some things that had to be equal under equilibrium. You got temperature, pressure, and what? Chemical potential. Okay. So if I'm in this region here, if I'm at a border, if I'm at the border or a triple point, then it's true that the chemical potential, here I have to think about this, of A in the gamma phase, the liquid phase, has to be the same in the beta phase, and it has to be the same in the liquid solid gas phase. Okay, now I mentioned that there can be more than one thing equal to, here I'll try to be consistent with my lettering. Okay, for ethanol, water, all the chemical potentials and all the different phases have to be equal. And now all we have to do is figure out how many equal signs we have. Which is a little bit of a puzzle. And I have to cheat a little bit because, okay, so what I can do is I can see that this looks like an area, right? Notice I drew a matrix. What's the length and width? What's the length? 3, because I have. I had 3. So in this case, I have to draw 3 components, right? Let me make Right. So I threw water and ethanol and some heroin. I don't know. I threw in some heroin. Shouldn't say this on the film anyway. Okay, so this is what? Now give me a letter.
C.
C. Okay, how many equal signs this way?
P.
Right, P minus 1. 2 phases gave me 1 equal sign. 3 phases gave me 2 equal signs. There you go. All right, now what this means is, do the algebra, and it's C minus P plus 2, which is called the Gibbs phase rule. Help if I can spell today. All right, I know I'm over, but let me point out how this works. I know I went a little bit over. Please come back. Okay, now let's go back to our ethanol phase diagram. Let's do this point right here. It is a 1 component, 1 phase, plus 2. Degrees of freedom are 2. That means I can change the pressure and temperature and maintain the singular phase. That means that this region is drawn as a plane. Okay, let's do this point. Okay, I've got 1 component because it's just ethanol. I've actually got 2 phases. I have 1 degree of freedom. That's a line. 2 degrees of freedom is a plane, 1 is a line. And if I do the triple point, then it truly is a point because points have no degrees of freedom. What about a quadruple point?
What does that mean? Negative 1 degrees of freedom?
I have minus 1 degrees of freedom. Well, you can't do that because then the world would be sucked into a black hole. So that's why you don't have anything beyond triple points. Okay, well, folks, that's really it. Next time, we're going to talk about how to put math, how to draw these lines in math. So, 10-minute break. I know I went over it. I know I always do that. Sorry.